Welcome to This Explainer. Look, today we're going to completely drop the math anxiety and decode the secret language of numbers together. If you've ever felt totally overwhelmed by alphabet soup terms like HCF, LCM, or prime factorization, you are absolutely in the right place. We're going to tear down those confusing textbook definitions and rebuild your understanding from the ground up using logic that actually makes sense.
So, let me ask you something. Are you ready to stop just blindly memorizing math and start truly understanding it? Because, let's be honest, memorizing a bunch of robotic steps might get you through one single test, but it totally evaporates from your brain the second you walk out of that exam room. When you actually understand the why behind the numbers, how they tick, you never really have to memorize the how ever again.
Okay, here's our game plan for today. We'll kick things off with 1, factors and multiples explained. Then 2, the power of prime. 3, decoding HCF and LCM. 4, the secret math formula. And finally, 5, conquering word problems. We're starting with the absolute basics and scaling all the way up to conquering those giant, scary word problems that usually make everyone freeze up.
Let's dive right into Section 1, Factors and Multiples Explained, the absolute building blocks of numbers. We've got to start with a strong foundation. So we're reframing two terms you have probably heard 1,000 times, but might still kind of mix up when the pressure is on.
It sounds like a simple question, right? What exactly is a factor versus a multiple? Well, getting this crystal clear in your head is absolutely crucial. It's literally the first step to unlocking every single thing we're going to cover today. Here is the easiest way to think about it. It's a binary distinction. Factors break a number down, while multiples, well, they build a number up. Think of factors as the puzzle pieces that fit perfectly inside your number without any leftovers at all. Multiples, on the other hand, are what you get when you take your number and just keep stacking it on top of itself over and over again, kind of like doing your times tables.
Let's make this super concrete with a real example. Take the number 8. Its factors are just 1, 2, 4, and 8. That's the whole shebang. There are no other natural numbers that divide perfectly into 8. But look at the multiples. 8, 16, 24, 32, 40, and on. So the key takeaway here is that a number has a totally limited, finite set of factors, but an infinite string of multiples stretching out forever.
Moving right along to Section 2, the power of prime, unlocking the DNA of all mathematics. Let's see how our basic building blocks form the very DNA of math itself. Because honestly, every single number out there is either a prime itself or it's just made up of prime numbers multiplying together.
The rule here is beautifully simple. If a number can only be divided by exactly two things, the number 1 and itself, it's prime. Take 2, for example. The only natural numbers that fit into it are 1 and 2. Same deal with 5 or 11. But if a number has a bunch of other factors dividing into it, we call it composite. Take 9. It can be divided by 1, 9, and 3. Since it has more than 2 factors, it's composite.
Now this is where it gets really interesting. The number 1 is literally a mathematical lone wolf. It's neither prime nor composite. Why? Well, remember the rule for a prime number is that it must have exactly 2 factors. The number 1 only has exactly 1 factor, itself. Since it doesn't have 2 factors, it's not prime, and since it doesn't have more than 2, it's not composite. It is entirely in a league of its own.
Okay, watch out for this one, because exams love to try and trick you here. They'll throw out the term coprime. Don't let the name fool you. Coprime just means two numbers that share absolutely no common factors other than 1. They don't actually have to be prime numbers themselves. Look at 8 and 9. We just saw they're both composite numbers. But what is the biggest number that divides perfectly into both 8 and 9? It's just 1. So because their highest common factor is 1, they are co-prime to each other.
All right, Section 3, decoding HCF and LCM, finding the hidden overlaps between numbers. With our definitions totally locked in, we can finally crack the code on HCF, the highest common factor, and LCM, the lowest common multiple. And we're going to do it without just blindly memorizing mechanical steps. Imagine you're asked to find the HCF and LCM of 144, 180, and 192 using prime factorization. Picture this grid in your mind. You break down each number into its prime bases, its 2s, 3s, and 5s. But here is a game changer of a trick to stop you from making mistakes. Notice how 144 and 192 don't have a 5 in their makeup? Just write in a 5 to the power of 0 for those missing spots. Anything to the power of 0 is just 1, so it doesn't change the math at all.
But visually, it perfectly aligns your bases vertically. It makes the rules we're about to use incredibly obvious.
Now that your numbers are perfectly stacked in that grid, finding the answer is a breeze. To find the HCF, which is the biggest number that divides into all of them, you just look down each column and take the lowest power of all the common prime factors. And for the LCM, the smallest number they all build up to, you look down the columns and just grab the highest power of all those prime factors. It turns a messy calculation into a super simple visual matching game.
Oh, and speaking of making things easier, here is a fantastic shortcut to keep in your back pocket. If you happen to notice that your two numbers are already prime numbers, let's call them P and Q, like 5 and 7, don't even waste your time calculating. Because they're prime, they only divide by 1 and themselves, right? So their highest common factor is automatically just 1. And their lowest common multiple? You just multiply the two numbers together. Boom, done.
Which brings us to Section 4, the secret math formula, the ultimate cheat code for real numbers. We are hitting the climax of our explainer right here. We're about to reveal a hidden relationship that connects every single thing we've talked about so far. Honestly, this part feels a little like magic if you don't know the trick.
Check this out. This equation right here is the absolute golden rule of math for two positive integers. If you have two numbers, let's just call them A and B, the product of their HCF and LCM is always perfectly equal to the product of the two numbers themselves. Now, quick heads up, it is vital to remember this only works for two numbers. Not 3, not 4, but for two numbers, this relationship is completely unbreakable.
This formula is literally a cheat code for your exams. If a test throws any 3 of these pieces at you, you can effortlessly solve for the missing fourth piece without breaking a sweat. In this scenario, we don't know the second number. Why? But hey, we know the HCF is 6, the LCM is 180, and the first number is 30. Just plug them in. 6 times 180 equals 1080. Divide that by 30, and wow, your missing number is 36. It completely bypasses all the heavy lifting.
All right, Section 5, conquering word problems, using our new tools to slice through exam anxiety. Let's take all these newly forged tools we've been talking about and use them to slice right through those complex, scary-sounding paragraphs that just look like a dense wall of text meant to confuse you.
Let's tackle a classic example. You're asked to find the greatest number that divides 85 and 72, but it leaves remainders of 1 and 2. The trick here is understanding what a remainder actually is. It's just a leftover piece getting in the way of a perfect division. So when a question wants the greatest number but throws in remainders, step 1 is simple. Just subtract those annoying leftovers right away. 85 minus 1 is 84, and 72 minus 2 is 70. Now you have numbers that will divide perfectly. From there, you just find the highest common factor of 84 and 70, which is 14. Simple as that.
On the flip side, look at this one. They want the smallest number that, when increased by 17, is exactly divisible by 520 and 468. Don't let the phrasing twist you up here. If it wants the smallest number exactly divisible by both, you are looking for the lowest common multiple. The LCM of 520 and 468 is 4680. But wait, the question asked what number when increased by 17 hits that target. So you just start at your LCM of 4680, and you subtract that 17 to find your starting point. That gives you 4663.
Before we wrap this up, you absolutely need to remember this one unbreakable truth to check your work during a test. Your HCF will always perfectly divide into your LCM. Every single time. The highest common factor is always a factor of the lowest common multiple. If you ever calculate an HCF and an LCM for a set of numbers, and that HCF doesn't divide neatly into the LCM, you immediately know a calculation error happened somewhere. It is an amazing built-in safety net.
Well, we have covered a ton of ground today, moving all the way from the simple building blocks of factors and multiples to unlocking the prime number shortcuts and slicing right through those tricky word problems. By understanding the actual meaning behind the methods, rather than just memorizing blind steps, you hold the keys to the secret language of numbers. So next time you're faced with a messy, chaotic string of data on an exam, what hidden patterns will you be able to find?